Statistical analysis.
Matrix.
You're still having trouble calculating it?
Yes. Because I can't get the HIIs.
Well, I just showed you how to do it.
I know you did. Well, that made me understand it a little bit better.
Yeah.
But before.
Yeah, before. Yeah. You couldn't get. You would have to take them off by hand. Okay. Before, but now it's kind of automatic, so you can calculate the HIIs, the SI squared. You can do all the influence and outlier analysis you want. You can put it on every problem now if you want. I guess some people probably even have a macro written for it by now. Okay? And other statistical packages will do that for you. Excel is not perfect because it's kind of do it by hand. And you have to keep writing in all these things over and over and over again as you go through this course. There's a lot of retyping the same stuff. But I figure at least you'll learn the theory a little bit that way. You have to figure out, you have to keep remembering what the hat matrix is and so on and so forth, instead of thinking, I need an HII column, an RI column, a TI column, and so on. That's too easy. And then just read the cutoffs and memorize the cutoffs and say, okay, there must be influence here. Okay. Anybody can do that. Okay. So that's not my main interest. The main interest is what you can do with multiple linear regression. What can you do? And then there's some side issues like experimental design, which we just touched on. There's some other things like a non-parametric approach, which is touched on. There's the question of transformations to try to get to the main assumptions, which we only talked about a little bit. Okay, the Box-Cox method, I think, is a nice additional thing. If you really want to see it, then we can do that too. But there's a logit model that's in Chapter 13. I wanted to get to that, and I thought maybe we should just go over this distribution theory a bit. I can hand out my notes on the distribution theory. We can start talking about that on Thursday before we go after the test or something like that, before we go to the next final week. And I'll just ask you to know a little bit of that stuff. So we're going to hand out those two sets of notes then. The Chapter 8, you just got those handed out. And here's the distributional property stuff that that's a lot of it's in the appendix, but not all of it. There's some 3 theorems in the appendix. Those are mainly the ones I'm going to want you to know, but I'm actually going to derive those 3 theorems in these notes. And why don't we just go ahead and look at those? I think you got one already.
I'll take another cut.
And
I brought it with me today.
And we won't talk about this today, but I'll just hand it to you. So please bring it next time or the time after. I'm pretty sure I'll get to it. Okay? It'll just be all calculations on the board. You learn a little probability. Okay. Just to give you the theory behind what an F-statistic is, so then maybe I'll never ask you what a moment generating function is again, but at least you'll know that there's something there that actually, so that you'll know that you know what things are supposed to be independent, okay, what things are supposed to be normal. Okay. Let's go on to Chapter 8. What we're going to do now is consider indicator variables in our models. An indicator variable is simply a variable with 2 values only, and those 2 values are 0 and 1. As we saw earlier, there are some values of variables that take only 2 values, minus 1 and 1, in the catapult data. Okay. That's not exactly an indicator variable. It's still a 2-valued variable, which is kind of important. But the indicator variable we have to distinguish indicator variables because they come in a special way in the models. Okay. Because they really correspond to a categorical variable. A numerical variable may have 2 values, minus 1 and 1 for low and high. Okay, fine. All right, but an indicator variable takes 2 values because it's indicating different categories of a certain variable. A categorical variable. What's a categorical variable? One where number has no meaning. For example, a tool of type A, sex. A tool of type A, tool of type B, was an example, or different kinds of cooling systems, air conditioners, swamp coolers, fans, what have you, okay? They're just different categories of things. Sometimes even a numerical variable can be turned into a categorical variable if there aren't very many levels of the thing. So, for example, I think in problem 811, which we're going to refer to later today, if I get there, you have one variable is the percentage of cotton in a fabric, and the dependent variable is the strength of that fabric, the tensile strength of that fabric. Now, there are 5 levels of the percentage of cotton: 15, 20, 25, 30, or 35% cotton in this synthetic, was a synthetic fiber, that's why. Okay? Now, that's not enough different values of the regressor to really try to make into a model, okay? And they're kind of like fixed qualitative levels, low cotton, less low, medium, So you could think of it as numerical values, and you still could try to fit and take those levels as numerical levels and try to make a function of strength with respect to percent cotton. However, there's not enough levels of the variable to really do that. Okay, so in that case, we make a categorical assignment as well. Okay, so that now we're turning that percentage of cotton turning a numerical variable into a categorical variable. So there's a possibility sometimes. So but sometimes you really can't turn a categorical variable into a numerical variable, period. Okay. So that's what we're going to study. We're going to study a problem of having a lathe, some kind of wood shop tool or whatever. I don't know if it has to be wood shop, but where else do lathes come in? I guess they might come up in machining other kind of parts, like metal parts and so on, for machines and so on. And depending on the lathe speed, the tool will have a certain lifetime, however that's determined. And so you want to know the relationship between tool type and lathe speed. And it's just a simple linear regression model. Okay, we're only going to try to fit a simple linear regression model to tool life. As a linear function of lathe speed. This is an example 8.1. Linear function of lathe speed, okay, but in 2 different types of tools. Well, why don't you just fit a linear regression to each one separately?
Because that doesn't tell you if they're actually different.
Well, yeah, you couldn't test hypotheses as to whether they're different or the same, okay, unless you put them all together in one linear model. So what we want to do is still be able to test hypotheses. So for type A, for tool type A, you're going to have, you might have a regression model of the form YIA equals alpha 0 plus alpha 1 xi plus an error. Okay, and for a tool of type B, you're going to have a model YIB equals, I'll just call it gammas because I'm going to use the betas later for something else. For the unified model, I'm going to use the betas for the unified model. Gamma 0 plus gamma 1 xi plus another error epsilon ip. Okay? I'm not going to say where the i's go for, they're just the ith observation. Okay? So you have 2 different linear models, in fact, and they show a picture. It's easy enough to show a picture. With Excel, it's a little harder because I'm kind of ill-equipped to handle Excel. But on page 270, they show the 2 different scatter plots for those 2 separate models. Okay, they show black dots and white dots. Okay, on page 270. And I'll try to show how I tried to make that plot with Excel. in a little bit. Okay. So, how would you, for example, there are two kind of natural hypotheses. One is that if I fit straight lines to each of those sets of dots separately, okay, right, I can fit straight lines to each of them separately. One question would be, are they parallel lines? Is alpha 1 equal to gamma 1? Okay. Since the same x's are being involved, so there's overlap. I think there is some overlap of the x's. Yeah, there is some. So, then you want to use the whole data set combined, okay, to test that hypothesis whether alpha 1 is equal to gamma 1. Okay? Because xi's are going to become the same here. So these are not just totally independent businesses. Okay? Because the xi's are in there. So I want to test whether alpha 1 is equal to gamma 1. That would be the parallel hypothesis, so you have parallel lines. Okay, and then you could also ask, well, maybe they're exactly the same line. Here, obviously, they wouldn't be in this picture. But then you can test whether both alpha 0 is equal to gamma 0 and alpha 1 is equal to gamma 1. Okay? You could also test whether they just have the same intercept, but they have different slopes. That's less interesting, perhaps. Okay? But certainly whether they're parallel, whether the tools are dying at the same rate. Okay? As a function of lathe speed. Okay. So one might be naturally have a longer life than the other for some reason. Okay, that would be a different intercept. All right, so this is, now how do I bring indicator variables in? That's the way I try to unify this business. Okay, in other words, put all the y values together as a column, and so on and so forth. How do I put this all together?
Well, are we already assuming they're parallel?
No, we have 4 independent parameters. We're assuming there's a different fit for each one in the full model. So how do I put that as an X matrix and all that? Here's the way I'm going to do it. It's going to be a matter of parameterizing in the correct way. We're going to have to choose the correct parameterization. What I'm going to do is I'm going to take beta 0 equal to alpha 0. So I'm going to introduce 4 parameters, but they're not going to be the same as these. Otherwise, this is it. Okay. So I'm going to put beta 0 equal to alpha 0. I'm going to take beta 1 equal to alpha 1. Okay. Then I'm going to take beta 2 equal to gamma 0 minus alpha 0, the change of the difference in the intercepts. Okay. And I'm going to take beta 3, the difference in the slopes. Okay. It's kind of obvious that those are 4 independent parameters. Okay. Given that alpha 0, alpha 1, gamma 0, and gamma 1 are 4 independent numbers, then these are, again, 4 independent numbers. You can play with linear algebra if you want. Okay. Show that the column space of a corresponding matrix, beta 0, in other words, parameterization. Actually, it's not parameterization because you can there's actually a word parameterization. It's a shorter spelling of the parameterization word. You can say either parameterization or you can say parametrization. Okay? It's a shorter version of the same word. Okay? I don't know if it came from the mathematicians or not, but anyway, they use it all the time. Okay? Parametrization. Okay, yeah, that's the spelling. So, you have this, and what does that give you then?
Well, okay, so then your model is...
Maybe I should just put a column. In other words, if I put A's and then B's, A, and then B, 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 B down here, like this, okay?
Then you do 0, 0, 0, 0, zeros, and then 1s for their feet.
Okay, let's see. So then I'm going to have, so my beta 0 column, and then I have a beta 1 column, and then I have a beta 2 column, and then I have a beta 3 column, right? Okay, this I'm not going to actually use for my data. I mean for my X matrix, but I'm going to have to key off it, okay? So what am I going to get for my X matrix? For the beta 0 column, I just have 1, 1, 1, 1, 1. Although irrespective A or B, okay?
Then you have your x's.
So what do I have? For beta 1 is alpha 1, so that's just the x's.
That's just all the x's.
All the x's, x1, x2, x3, and so on, all the x's that I have up to xn. Okay? Okay? Then I have for the beta 2, what am I going to put in here? I need to pick up, okay, what this is showing is that, so far shows that beta 0 plus beta 1x. When I'm going to have my X matrix and I have my beta matrix. Is simply beta 0, beta 1, beta 2, beta 3. So I'm going to be multiplying this matrix times this column to get my model for means. Okay? So what am I going to need to put in for this beta 2 column? Okay.
0, 0, zeros.
Okay, let's see. I need to... Beta 2 is, according to this definition, is the difference of the intercepts. Okay, I don't want to put a difference in. Right? I don't want to go from alpha 0 to gamma 0 from the type A's. So I'm going to put zeros here. Down to 0 here. Right? But then after that, I do want to put in the difference. I want to put in the different intercept. So I put in 1s here. Now what am I going to have to do for the last column?
Same thing, just put xn in there, or xk through xn in there.
Okay, so this is, so it's zeros here. I don't want to put in the new slope if it's type A, but I do want to put in the new slope. So what does it mean? I need, if I call this x, I don't know, I didn't give a notation for that like Shane was saying. I didn't really give a notation for it. So if I call this x sub n1 plus 1 or something, okay, if they're n1a's and n2b's, where n1 plus n2 is equal to n, okay, I could call this n1 plus n2 equals xn equals n1 plus n2. All right, so that n1 of these, if I need it, I don't really need to put a notation, but I will here, okay? Then I will call this, then I'll have this put as x of n1 plus 1 again is all, down to x of n. All right, so I put zeros here, but then I put x values here. Why is that?
So it's almost identical to our spline model.
That is because let's take this row here times this column. Okay. Yeah, you do have indicators multiplying things, but you don't have the indicators themselves in this. Well, you do have some indicators themselves in the spline model, depending. Yeah, it's very similar looking. So you look. Suppose I multiply that times this. What do I get? I get this row times this column gives me beta 0 plus beta 1 times x n1 plus 1 plus beta 2 plus beta 3 times x n1 plus 1. Okay? Now some of these x's can be repeated too, by the way. Alright? This is just, I had a tool B at this x level, but I had tool A at the same x level, so this x n1 plus 1 might equal x1. Alright? So these x's don't have to be distinct here. Alright? So what is this telling me? That means I've got intercept beta 0 plus beta 2. And I've got slope beta 1 plus beta 3. Okay? I just put x instead of putting all that extra tackle on there. Okay? So that means I've got a different... So that's different than, for example, the beta 0 plus beta 1x. Okay? Versus if I put in this row, okay, times this column, I get beta 0 plus beta 1x, okay, is my regression line. So you see how the betas are. The beta 2 is the change in the intercept. The beta 3 is the change in the slope. Okay, so that makes it easy to test the hypothesis that the slopes are the same. You just take the hypothesis, to test the hypothesis that the slopes are the same, you just set beta 3 equal to 0. To test the hypothesis that both lines are the same, you just set both beta 2 and beta 3 equal to 0. So H naught beta 3 equal to 0 means parallel lines are holding. This is the submodel of the reduced model where parallel lines are holding. Okay? Okay? And H double naught, I guess, beta 2 equals beta 3 equals to 0 means lines, coincident lines, hold. They're both the same line. Okay? So you could test those hypotheses using the x2 sum of squares method. It's no big deal. You just have your x matrix here. So the only question is how do you construct your x matrix? And there it is. Okay. So I argue that how many indicator, okay, there's one indicator variable. Now I'm going to write this as a different way. I'm going to call this variable, I'm going to call it D in order to keep it from calling it an x. So if I call that a D, an indicator variable, all right, then what does this model look like in terms of, it looks like a quadratic, it's kind of like a quadratic model, but there's no d squared because I don't need to put in d squared because d squared is equal to d. So I'm going to have this. It looks like this. It looks like y equals beta 0 plus beta 1x plus beta 2d plus beta 3 dx or xd. Okay? And there's no, because I'm only considering linear in x. I could go x squared d if I wanted to consider quadratic in x. But I'm never going to consider, well, I don't have to put a d squared because d squared is equal to d. So that would be giving me too many parameters, right? It would just, and I don't put in xd squared because d squared is equal to d. So d only ever comes in the first power. So that's what it looks like. So this is the interaction term. In other words, if tool type interacts with lathe speed, is one type of tool live longer, tends to even at higher speeds, okay, versus the other one, okay? Is the slope different? Okay. So one tool type likes high speeds, okay, versus the other one. Okay. That's the interaction term. Okay. Okay, suppose I had more than two categories. All right, so there was one. Okay, the point is that there was only one indicator variable when I have two levels, right? How many indicator variables would I have if I had three levels? Two. How do you know that?
They're red.
Oh, you read. Okay. And so on to the kth level. The reason is you wouldn't have more. Why would you not have more? For example, if I'm having, we'll assume an intercept. If I had, in order to, how would I do it if I've got two levels? Let's look at, what was the example I was going to do for that? The two-level case. Here it is. Problem 813. the quality of the Pinot Noir wine. Okay? Quality of wine, which we looked at maybe once before in problem A13. What they're going to do is we're going to study the quality of the wine as a function of flavor and region. Okay? So in problem A13, okay, more than one indicator variable. You're going to have quality of wine. You're going to have flavor. That's my X. That is a numerical value. Okay? The flavor is rated somehow on a numerical scale. Okay? So that is a numerical variable. You can see how maybe that would be more likely to be a categorical variable, but here it is a numerical variable. Okay, and then you're going to have region of the wine. And that's going to be 1, 2, or 3. Okay? So the 3, that's obviously a categorical variable. Okay? What you're going to do is you're going to consider just a regression. You're going to consider flavor as only a linear term. Okay? In the regression, and you're going to bring in the region. Now, how would you do it with more than one regressor? So similar as to the 2-life problem. How would you deal with 2 regressors? So now you're going to have 3 possible simple linear regression lines depending on the region, right? So now you'd have X and you could have Y, and you'd have the wines of region 1, you'd have the quality versus the flavor, okay? And then you'd have the wines of region 2, and you have the quality versus the flavor, okay? And you have the wines of region 3. They still have flavors that overlap, obviously, and you have the quality versus the flavor. Okay. So how do we set that up? What's the X matrix? I've got it shown on page 4 of these notes. What I'm going to do is introduce 2 indicator variables. So I'm going to put the region here, and then I'm going to put indicator variable D1, and then I'm simply going to be, there's not going to be any change. I'm going to take the first line, which was the dots here, okay, and basically say that's the beta 0 and the beta 1 are the slopes, the intercept and the slope. This is just the parameters of that line, the intercept and the slope. So this is beta 0, okay, and the slope is m equals beta 1 of that first line, okay. So I don't need either of my indicator variables to be anything but 0 at that point. Okay? Because when I don't want the corresponding other parameters to come in to the equation for y. Similar as over here. So then what do I do? If I want, now for the second line, the one with the boxes here, I want, now what should I have for the intercept here? Now I'm going to take beta 0 plus beta 2, okay? Beta 2 is going to be the change, okay, from the initial one. And then I think for the last one, the way I'm going to do it is I'm going to do beta 0 plus beta 3. So it's going to be the change from the initial intercept, okay? I believe that's the way it's done. Okay? So I'm going to have my betas over here. Well, so now I'm going to have my X matrix. You're going to have my column of 1s. And this is indicating also, why wouldn't I have a third indicator variable? Well, also the indicator variables are not going to well, let's see here. See, I'm going to put 1s here so that I pick up my beta 0, my beta 1, my beta 2, beta 3. I need 6 parameters, beta 4, beta 5, right? Because there's 3 lines. Beta 0 and beta 1, so my x's, x1 down to xn. Dot, dot, dot. These are 1s. Beta 2. Well, I'm going to want to pick up all zeros here, right? In region 1. I don't want any of the betas 2, 3, 4, or 5 to come into the equation. Right? We pick all zeros here. So then what are they going to change? They're going to change here. I'm going to want my I'm going to want beta 0 plus beta 2 to be my intercept, so I'm going to put a 1 here, right? And I want my slope to be beta 1 plus beta 3, okay? So my slope here is going to be beta 1 plus beta 3. That's the way I'm going to set my betas up, okay? So beta 3 is going to be the change to slope 1. And so that's going to be in there, so I need an x there. So I call this x of n1 plus 1 again, I call this x of n1 plus 1. So I need the indicator times the x. But now if I get down here to region 3,
that's going to be 0.
Well, no, I guess I'm still going to hear it. So x n1 plus 2 and so on down to x n1 plus n2. Okay. So then I'm going to have, because that's always the way it was. This always was the x column. I'm going to have 1, 1, 1, 1, 1. And then I'm going to have this is down to x n1 plus 1 plus 2 down to x n1 plus n2. Then I'm going to have, I want zeros here again, right? I want zeros here because I don't want to pick up any of the other betas. I do want to pick up beta 0 through beta 3, all right? Because I want to have beta 0 plus beta 2 as the intercept and beta 1 plus beta 3 as the slope. So I need all those 4. Then when I get down to the final in region 3, I need all 6 parameters involved. So let's see. But I don't want all 6 parameters. I'm only going to have 4 parameters involved again because now it's going to be beta 0 plus beta 3 and beta slope equals beta 1 plus beta. I'm sorry, beta 0 plus beta. I'm sorry, this should have been beta 4 now because of the way I'm doing this. Did I do it right? What are the 3? Let's see what I did here.
So you're using beta 4 and beta 5.
I'm going to use beta 4 and beta 5 here?
Yeah.
I see. Did I... Yeah, I made a mistake here. Because what I'm going to do is I'm going to stick in it... The way I'm going to do this... I'm going to put beta 4 as the slope here. I'm going to use... here, beta 4, and then I'm going to go to beta 5 here. I'm going to use beta 3 as the other intercept parameter, the way I'm doing it. Okay, I'm sorry. This should have been 0, so I should put xn plus 1 here, xn1 plus n2 here. Okay? So I'm going to do it. First, I'm going to put in the indicators, because this beta 3 column is going to be an indicator column. First, I'm going to put the indicators, then I'm going to put the interactions. So the way I'm doing this is I'm going to save the slopes, the change in the slopes for the last 2 parameters, beta 4 and beta 5. So that makes beta 2 and beta 3 the change of the intercepts. I was kind of like leapfrogging before. I don't want to do that leapfrogging. I'm just going to keep the slopes at the end of the scale and the intercepts in the intermediate. Okay? So then what do I put here for this last row? I put zeros here because I don't want the beta 2, the change of the... beta 2 was the first change of intercept. Beta 3 is the second change of intercept. I do want that. Okay? Second change of intercept. And then I don't want the first change of slope, but I do want the second change of slope. So I get then the xn2, 1 plus n2 plus 1 down to xn here. Okay, so what am I getting all together? These columns can now be labeled as 1, x, D1, D2, XD1, and XD2. So now the columns are 1, X, D1, D2, XD1, and XD2. I think I wrote a D1X and D2X, but it doesn't matter. Okay, so it means I multiply this X column by this. This is the D1 column. I just multiply this times this. Okay, to get this fifth column here, and then multiply this times this indicator column to get this sixth column. All right, so you can see how the two of the columns are the products of the previous of this one times this one and this one times this one.
And Dij is always going to be 0.
What do you mean Dij? Oh, D1, yes, right, Di times Dj, Di times Dj as a product. This is product here. You can put times sign, okay, is equal to 0 for I unequal to j. The indicators are orthogonal. Okay? And also, that's why I don't put a third indicator. What if I had a third indicator where there were one? You don't see any ones in the beginning, right? Because if I added those three up, they equal the column of ones. So the column of ones is accounting, for the absence of another indicator, or vice versa. All right. So you don't want linear dependence in the column. So this is where the indicator is set up. Now, unfortunately, the author changes when it gets to the single factor analysis of variance. How is he going to handle this? Okay. So why don't we go talk just a little bit about that, and 5 minutes about that. And I'll just tell you how it seems a little bit different. Put the clock on. In 5 minutes, we're going to quit. Okay. Okay. 4.5 now. Okay, so what I want to talk about is that cotton versus fiber strength example. How do I model that using the same technique?
Where's the data for that one? Is that
it's in problem 811. Bless you. And actually, I put an example on the website as well for that problem. So I have like 6 new examples on the website. One of them's a little bit old because that was problem 511 and still playing with that thing. Okay. So problem 811, you've got 5 different levels of cotton. Bless you. And what I'm going to do is in order to put the data in columns, I'm going to transpose the data the way he's got it in the book and show it as I have it on page 7, I think, of these notes or so. Yeah. I will note there is one comment I would make about this problem 813 before I go on, and that is you don't want to use region as a regressor. I did make a comment about that. If you use region as a regressor instead of this, in other words, if you used, here was the note on the top of page 5. If I put in, suppose I didn't have the interaction term. Okay, so I had the parallel lines model. If I have EY equals beta 0 plus beta 1x plus beta 2 d1 plus beta 3 d2 is not equivalent to EY equals beta 0 plus beta 1x plus another parameter, beta 2 region. Let's put in flavor, beta 1x plus beta 2 region, where region takes the values, coded values 1, 2, and 3. Okay? So you might say, well, why not just put that in? It's an additive model. Region has values 1, 2, 3. You just plug it in. Okay? I have 3 parameters, not 4. What is this business with indicator variables? Why not do this? The problem is this. What you actually get is when region is 1, you get a different intercept. Okay. Which is all this is doing. It's giving you different intercepts.
Saying the difference in intercepts would have to be the same between region 1 and 2 and region 1 and 3.
Region 2 and 3.
2 and 3.
Yeah. So what it really give is that you'd have one line, and then you'd have another line parallel, okay, which is already what I'm assuming here, that I get parallel lines. But now, between region 3 and region 2, this is region 2. Let's say the flavor was going up, okay? I mean, the quality was going up by region. Then in region 3, yeah, I mean, that's the whole point, is that it's got to go up exactly the same amount again. It doesn't, in fact, it can't go down. It has to go up again, okay? So not only can it not go down, but it has to go up by the same exact amount. So this difference height change would be beta 2. This height change here would be beta 2 if I call this, let's call it beta 2 star. Okay, to distinguish it from that beta 2. Okay? So they would be parallel in a very lockstep fashion. So they clearly would not be what you would want to model. You're not really trying to model that. Okay, you're trying to say, I want parallel lines. All right, but not in this way. Okay? So that's the danger. Don't use region as the actual regressor, even though it's got nice values 1, 2, 3. Okay?
Now, in this Cotton model, why would we even think of using it as a indicator variable?
Well, because I said there's too few levels.
Okay.
There's too few levels. There's only 5 levels. So, what the one-way analysis of variance, or they calls it also call it the single factor Anova, is a very simple situation. What you have is you have some categories which might actually be defined by a numerical variable, as it is in this case, cotton percent. And I'm going to transpose the table. So that the data comes in columns. And so then I have, instead of rows. So at the 15% cotton level, you have the strengths are 7, 7, 15, 11, and 9. Oh, the bottom of the page got cut off. You can't see the Y bars. I'll have to remember what they are. They're 10.8, 15.4 for the sample averages. Y bar equals 10.8, 15.4, 17.6, 21.6, and 10.8 again. No, this is 9.8. 9.8. Okay. So the strength got bigger and then dropped down again. Okay? So you can see you're going to at least need a quadratic or a cubic model to try to fit this, and there's only 5 x values. How are you going to do that? There's too many parameters to try to fit. Okay? So that's not going to be all that useful. Okay? The meaningfulness of the parameters won't be. There won't be any meaning to the parameters that you're estimating. You try to just fit a cubic or quadratic polynomial to 4 points. It's an exact fit. Right? That's not going to work. So we can do an exact fit much easier. Just take the Y bars. Okay? And those are the points I want my quartic to go through. Okay. All right? So, you won't have an exact fit, no, because you got 25 data points. But basically, you know, if you were going to put the betas in, you'll get your quartic model with going to the points x, y bar. Okay? Roughly speaking. So that's not going to give you anything different than just the y bars. See what I'm saying? There's not enough x values. Anyway, these were the y values. And they call these yij. So I actually, in this case now, is the treatment level. I equals treatment index. Treatment level index. I goes from 1 to k, which here would be 5. There's also 5 repeated observations in each column. So that's unfortunate that the number of treatment levels was equal to the number of repeats, but it just so happened in this case. So these are the treatment levels. So those are the categories, right? You might have corn of different hybrids and you're looking at yields, right? As an agricultural example. There's no way to, those are just hybrids. How can you compare one hybrid to another numerically? Okay? So here, the cotton percentage is just the stand-in for a treatment level. Okay. So how do you deal with this? What's the actual model for means? What you do is you give a different mean for each of these columns. So this is mu1, mu2, mu3, mu4, and mu5. Those are the means. You actually give a different mean for each column. All right? And that's your model. So Yij equals mu I plus epsilon ij. J goes from 1 to some number of repeats. Here it was, and I could have a dependent I and even. So these don't have to be balanced columns. Okay? I could have 7 observations at cotton level percent 15. And I could have 5 observations at the other ones, for example. You wouldn't have to have the balanced array. Here, Excel is going to assume you have a balanced array if you use the Anova, I think. Or maybe not. It may not assume balanced, but yeah, it's typically balanced. Okay. So you just say those are the model for the mean. Just mu1, just different mean for each treatment level. Period. What else is there to say? How can I turn that into a regression model? You could have studied this in your first course in statistics, in fact. Many of you did. How do you turn this into a regression model? Well, with indicator variables. In other words, if you want to handle it with multiple linear regression, you say, okay, there's going to be one mean for this column of these y values. Then there's going to be a different one here. Okay? That's a beta 0 plus a beta 1 d1. All right? And then I have a beta 0 plus a beta 2 d2, a beta 0 plus a beta 3 d3, and a beta 0 plus a beta 4 d4. Okay? So, but now the d's have to start with 1s in the first place and not 0s in the first place. Okay? Because I need in the first column of data, in this, actually I don't have to have it that way, but that's the way the author does it, strangely. In other words, he calls mu1 beta 0 plus beta 1 d1, where d1 starts with 1s. Okay, so that's the thing that's strange about the way the author did it. I don't like the way he did it, but I'll live with it. You can do it millions of ways. So what the author says is that I'm going to take first, the standard way to write this is mu plus tau I. So he's going to write mu I equals mu plus tau I. Now that's 6 parameters. I goes from 1 to k, which in our example is 5. And that would be too many parameters. So actually, for the classical parameterization, you have a grand mean, sort of an overall mean, mu. And then you basically say, okay, this 9.8 is a reflection of a grand mean plus a change. Okay, so you actually put the change equal across the board. All right, there's some mysterious grand mean, and then this is mu1 equals mu plus tau 1. This is mu plus tau 2, mu plus tau 3, mu plus tau 4, mu plus tau 5. That's 6 parameters. We're out of time. So what you have to do here is put summation tau I equal to 0. So with this parameterization, you have to put a constraint on it. So the dummy variable approach is more logical from our point of view, perhaps, from the regression point of view, and that is to put mu1 equal to beta 0 plus beta 1. I don't know why it does it that way, but mu2 equals beta 0 plus beta 2. Mu3 is, let's see if I get this right, beta 0 plus beta 3. Mu4 is, let's see if I got it right. Yeah. Mu4 is beta 0 plus beta 4, the way I did it here. And then mu5 is just your beta 0 again. You got your beta 0 free, right? And he puts that as mu5. Okay? Instead of starting with mu5 and counting up the other way. So if you do it this way, then your indicator variables have to start with 1s in the first place. So in that case, if I counted these y's down from the top, 7, 7, 15, 11, 9, 12, 17, 12, 18, 18, and so on, all the way down through all 25 of them, all right, in terms of your column of y's, then your X matrix would look like 1s, and then 1, 1, 1, 1, 1, 5 of them, and then zeros, and then zeros. So you start with 1s in the first rows, okay? And then zeros the rest of the way. And then 0, 0, 0, zeros down to here, and then 1s for a while, and then zeros. So there's going to be 5 different situations here, right? 1, 2, 3, 4, and then I need one more. 1, 1, 1, and then zeros here, zeros, zeros, and then just one more indicator. Just 4 indicators. Let's see, 1's here, and then zeros. So this is X, this is D1, D2, D3, well, different ones. He's calling them X1, X2, X3, and X4 now, because they're different indicators. Okay? It's a little bit different than the D's. All right, the author calls them X1, X2, X3, and X4. Okay? You don't put X5, because if I added the X1 through X5, it would equal the 1 column. So you have 5 parameters for the 5 means. Right? So there's a beta 0 through beta 4. So that's how you can do one-way analysis of variance, give a different mean for each model. The hypothesis that all the taus are equal to 0 is still just the hypothesis that all the beta 1 through beta 4 is equal to 0. So H naught tau I all equal to 0 for all I is equivalent to H0 beta 1 equals beta 2 equals beta 3 equals beta 4 equals to 0. So because these taus are not independent, there's one constraint. And there's 5 equal zeros here, but there's only 4 equal signs here. In other words, there's only 4 degrees of freedom for this hypothesis. So you have to keep your wits about you. There's only 4 degrees of freedom for testing this hypothesis in the corresponding SSH. Right? SSH has 4 degrees of freedom. Okay. We'll look at this next time. We'll review this example a bit next time when we get here. Okay? On Wednesday. Why don't we call it a